everyone, this is Jill Hurston from Accelerate. Welcome to our Zip Chat today, episode 14. With that, I'd like to introduce our host, Mike Watson. He's our SVP of Engineering at Accelerate. Mike, handing it over to you.
Thanks, Jill. Welcome everyone today to our Zip Chat, episode 14, which is Observability and DevOps. Just a brief introduction for me. I'm the Senior Vice President of Product Engineering here at Accelerate, and I've been doing engineering leadership for quite a long time, and there's a wide range of topics that interest me, including this one. I'm excited to have with me today Will Capelli. He's a DevOps specialist with Splunk, and I'm looking forward to a great conversation. So let's jump into a quick poll to get started. Don't mind throwing that up. Technical challenge.
Here we go. I know.
Oh, here's a poll. We'll get into that later. So
okay.
Quickly, for those of you that have joined us, let us know your interest in observability. I know I've been in all three of these categories at one point in my career or another, so we'll just gather the poll results real quick. Yeah, so Will, while we're waiting, how are you today and how are you feeling about this topic?
Oh, hi, Mike. Yeah, I'm doing quite well today. Thank you. And yeah, actually, to be right now, I find this one of the most interesting topics in the IT industry, actually. I mean, we'll get into later what exactly observability is and why it's important and why it's important to DevOps. But, you know, I will say that kind of many of the interesting trends in IT that we've seen over the last couple of years, and even some of the trends that have been accelerated and exacerbated by the pandemic, you know, really all come together into this topic of observability. So I'm very excited to be talking about this with you today.
Yeah, so this is about what I expected in terms of distribution. Yeah, most people have their environment in pretty good shape, but always interesting to understand that. So we can get into that more later. So Will, when I think about DevOps, it's kind of a broad spectrum. I have conversations with different people, and you know, they use that term in different ways. Like sometimes it's like, oh, I have a DevOps engineer, meaning it's a role, you know, but it's sometimes it means you know, other things. What's your thoughts on what DevOps means?
Well, you're right. It's a great question, and I mean, it's interesting that a category that, you know, has become so important for the market really doesn't have a canonical definition. I mean, the analyst communities have not articulated clearly what it means to be DevOps or what DevOps is. So we're all kind of left on our own to try to understand what it means. The way in which I look at it is that, you know, DevOps is, you know, names a culture that is involved in the attempt to continuously deliver new functionality, new components into a production environment. And then, you know, with that as the center, that focus on continuously delivering new functionality into the production environment, there come the changes in processes and practices that entails, and then also the technologies that will support that ability to continuously deliver new components into the environment. And in a way that kind of seems almost like, you know, just an incremental change over past development management practices that IT organizations have worked with, you know, for 50 years basically. But the truth of the matter is that this focus on continuousness, this focus on speed, has in fact kind of radically changed all of IT. And I think we'll get into some of those dimensions of change today. But once again, the critical thing is kind of a shift from looking at application development and functionality delivery as a more or less kind of occasional event, right, to looking at it as a continuous event. And the consequence of that is looking at the production environment not as something to which changes happen on an occasional basis, but looking at the production environment as something which is in a continuous state of flux.
Yeah, that makes sense. Yeah, because it is sort of speed to delivery or speed to deployment is is a huge trending thing, and some folks are good at it, and some folks are not good at it.
Oh, absolutely. No, I never said it was easy to achieve, right? Nor, nor you could argue that almost no firm, vendor, or IT enterprise has actually achieved, pure continuity of delivery across, their entire application portfolio, right? So yeah, it's definitely an ideal to which, we as an industry are aspiring rather than something that we've easily achieved, for sure.
Yeah, that makes sense. So in this new kind of culture that you're calling it, I've noticed that there's this tendency, like I mentioned, to call someone a DevOps engineer or like the DevOps role or whatever. So what are your thoughts
Right.
about what are the roles that are evolving in this new culture?
Well, I think that I'm not going to say anything, terribly profound or shocking here. I think that there are what we're seeing within DevOps is two fundamental roles emerging. One is the DevOps software engineer, who's basically an evolute of the classical application developer, right? And the only difference, and if you will, between a DevOps software engineer and the traditional application developer is once again that emphasis on the kind of continuous delivery of new functionality into the environment rather than the occasional delivery of that functionality. And then kind of as a footnote to that, but a very important one, in fact, it's what puts the ops in DevOps, it is the recognition that precisely because you are tasked to deliver at that kind of velocity, you also need to take over at least some of the responsibility for managing the components that you've delivered into that production environment. So you can't just throw that component over the wall and hope that someone in IT operations will take care of its functioning in production. You yourself or your team, as a deliverer of that component, the production environment also has, as I say, at least some responsibility for that for that component's health once it's out in the production world. So that's one of the two key roles. The other key role, which we've seen really explode, at least in terms of kind of job titles over the last couple of years, and in fact, actually. Over the course of the last 18 months, over the course of the pandemic, I've seen requirements for this role really take off, and that is the SRE, or Site Reliability Engineer. And the Site Reliability Engineer, they in many ways are the evolute of the traditional IT operations professional, the people that are tasked with caring for the infrastructure that supports the production environment that is receiving all of these new components and is ensuring that these new components are processing effectively. But of course, just as the application developer within the kind of DevOps atmosphere has now kind of taken on some management of production environment responsibilities and has kind of changed their role somewhat due to the speed that is required. Likewise, the Site Reliability Engineer in some ways is not just there to manage a static infrastructure, but is rather ensuring that the infrastructure itself is evolving, right, and is changing, and is ensuring that new functionalities are delivered into the infrastructure supporting the production environment. So in a sense, that descendant of the IT operations infrastructure manager has taken on some characteristics of the developer, right? And so, and yet another reason to call it DevOps, because that individual is doing, yes, primarily you could say operations related work, but also, and the concept of infrastructure as code plays in here, is doing some development work as well. And then of course, how should I say, the punchline here is that even though we've definitely seen kind of DevOps, if you will, kind of split into these two roles of software engineer and site reliability engineer, the truth of the matter is that when we look at these digital stacks that are being delivered, that are composed of infrastructure elements and kind of application elements, the line between infrastructure and application actually is kind of blurred. So I would ultimately say that the difference between software engineer and site reliability engineer, although a reality, is actually kind of a continuum that stretches from kind of more application-like concerns to more infrastructure-like concerns. But unlike in the old days where it was very, very easy to identify what's infrastructure, what's application, so on and so forth, those distinctions, are at best now approximations rather than hard and fast realities.
Yeah, that all makes sense. So it's kind of ironic that we've tried to blend these organizations and they end up basically with the same roles. There's a lot of resistance there, I guess.
That's right. That's right.
And I don't mean human resistance, just like maybe those roles are really real things, regardless of how you organize. The one thing that I've seen in the trend is it's less likely now to have those two groups under separate leadership, because it used to be you'd have a production.
Yeah, that's right.
Operations, and then you'd have development, and they didn't work close together, and there was a large wall between them, and their objectives might have even been different. And so I think this DevOps culture helps bring all of that together, which is useful.
Yeah, I think that's absolutely spot on. That yeah, in a way, the breakdown of the organizational barriers is probably one of the most significant aspects of the development, and also in my experience, one of the most, how shall I say, kind of difficult things to get right in a lot of enterprises, and that the cultural shift that is required to kind of adopt DevOps is profound and is very, very difficult for many large enterprises, particularly large enterprises, to affect. So kind of breaking, and of course this is true in many other areas as well, but kind of breaking down those silos, breaking down those barriers, is often like one of the hardest things it is to get human beings to do, and that happens here as well.
Yeah, makes sense. I think if you're struggling with this, I mean, obviously co-locating the site reliability engineers into development teams is a great way to sort of start that as a ground up type of approach versus top down, because if you make the objectives for those folks equivalent, meaning good, healthy, secure production environment with working features all the time, and you have them work together, I think you can get that result pretty easily. Or it definitely.
No, I think that's absolutely right. I think that's absolutely right.
All right, so let's move on a little bit from. So now we have a good definition of DevOps. Let's talk about observability. So, in talking to you before and thinking about this, I think observability is sort of an evolution of monitoring, or traditional production monitoring. So let's start with kind of understanding how traditional production monitoring works from your perspective.
Yeah, sure. No, it's a great question, and and I'll start out by saying, I mean, there's even debate in the market as to whether or not observability is indeed something new, right? And there's a lot of let's call them cynics, wise folks that say, oh no, it's just another term for monitoring that the vendors are slapping on their products to try to make them relevant for another decade, right? And it's certainly true. Vendors, and I'm one of them, do have a penchant for trying to find new cool names for, under which they can sell old technologies. But I do think that a very strong case can be made that in order to deal with the kinds of systems, and we'll get to this later on, that are produced by a DevOps culture, a genuinely new approach to monitoring, needs to be engaged, and and observability is actually a good name for it. Both because I think it describes things, quite well, and also because it does allude to, and it does. I mean, historically, the reason why the DevOps community chose the term observability is because of the roots of the concept of observability in control theory, and it all kind of weaves together. We'll get to that, but I think, and I think this is your point, Mike. In order to understand why we needed that new paradigm, right, we really need to understand, in some sense, what ails traditional monitoring technology. Why are the tools that are still widely used today, why are they ineffective with regard to the digital stacks, the applications and infrastructure produced under the aegis of DevOps culture? And I think that to understand how they fall short, let's understand how they all work. And I think this is true of pretty much any application performance monitoring tool, infrastructure monitoring tool, network monitoring tool that is currently available on the market, or at least most of them. And the first concept you need to have in mind is, of course, the idea that digital stacks, both old and new applications, both old and new, generate an enormous amount of self-descriptive data. And in fact, when I was at Gartner, one of the last things that I was doing was looking at just how much kind of self-descriptive data was being generated by these applications and infrastructures. And I mean the metrics, the traces, the logs, the event records, all this stuff that just gets generated in the course of a digital stack going about doing what it was designed to do. And there's no question that the volume of that data has grown tremendously. And what my research was telling me was that volume was increasing by an order of magnitude pretty much every 5 years. And then, going back through history, I concluded that by the time we'd gotten to 2020, there was a gigabyte, right? GEGO byte, that's 10 to the 27 bits of self-descriptive data being generated by digital stacks. And there was another aspect of that research which I thought was really interesting, that not only were we dealing, by the time you get to 2020, and now 2021, it's even worse, with vast volumes of data, but that data is incredibly noisy, right? As much as 90% of that data that IT operations teams, that DevOps professionals are dealing with is either kind of duplication of other data or is just plain noise, just kind of, random things that actually mean nothing. So you've got this vast volume of data being generated by your applications, by your infrastructures. Now, faced with that, traditional monitoring tools, and once again, didn't matter whether targeted applications, infrastructure, network, even end user experience, databases, all the domains that were monitored. What they basically do is sample, some of that self-descriptive data, because it just seems so voluminous that the idea of ingesting all of it, is just downright crazy and expensive, and based upon sound statistical theory, not necessary. You just get a good sample, the way in which they kind of test the efficacy of vaccines, right? Get a small little sample of people and And you know that if the population has a certain kind of properties associated with it, looking at 1% of the total data can give you a pretty good idea what the entire data set says. So they would start by sampling. Then the second aspect of it is that in order to interpret what is being sampled, I shouldn't use the past tense because most of the tools out there work this way right now, right? Within the performance monitoring tool itself, in some way or another, some mode of representation or another, there would be essentially a model of the environment that was being monitored. And this model could be built by the user, it could be discovered in an automated way, it could be written in rules, it could be done with a topology diagram, but there's some kind of model of the environment sitting in the monitoring tool. So that's your setup. And then what would happen is that effectively this model predicts the data that the system is going to be ingesting. So it takes the samples, matches it against what the model predicts, and if indeed the sample accords with what the model has predicted, then everything's fine. You get a smiley face on the screen. Basically, we usually get lines, graphs and that kind of thing to keep you watching to make it interesting. But the bottom line is that nothing terrible is happening, nothing surprising is happening in your environment. Just keep watching the river flow. Of course, if the sample does not match what the model predicts, then something's going on, and you get an alert. And so basically at the end of the day, this kind of predefined static model matched against sampled data is how most application infrastructure, network monitoring, and event management systems, by the way, work. That's the basic structure. Now, this is beautiful, and it worked for, it was effective, or so we think, for a couple of decades, actually. But the efficacy of that architecture, really began to come unstuck. I'd say, around 2015, when you took your applications that were kind of built in Java or .NET, and they'd been maybe 1,000 objects that would be associated with them. Remember, object-oriented programming was the programming paradigm du jour at that point. And you had maybe around 1,000 objects in a good program. And but around 2015, the number of objects really began to multiply. And then we began to shift to other architectures, microservice, container-based architectures. And now we're kind of at another turn in the wheel, and we're shifting to serverless, function-based architectures, right? And what this means is that the digital stacks have become, a lot more modular. They're built out of a lot more components. They're a lot more distributed. I mean, applications and infrastructures, now literally, particularly if you take the cloud into account, you're talking about components that are literally kind of spread across the surface of the earth. And even if you're thinking about the kind of the GPS elements of many applications, up into the atmosphere as well, right? So you've got incredibly what appears to the user or the customer as a single integrated application or service is in fact making use of components that are kind of spread all over the place, right? They've also become a lot more dynamic in the sense that, I remember talking about the old monitoring model, there was kind of a static topology or a static structure that described the system. Well, no more, because in a container-based environment, microservices, the message paths are continually shifting, the topology of the system is continually changing. I mean, to the point that even to talk about topologies in the old way doesn't really make much sense. And then finally, they become a lot more ephemeral at the component level. I mean, if you go back even, let's say, 5 or 6 years, you were talking about, virtual machines that, seem pretty ephemeral at that point because they lived for a month, right? You would spin them up, use them, and spin them down, right? And you'd usually pay for them by the month. So their shortest lifespan, they would kind of live for a month. And then you kind of move to kind of a world of microservices and containers where you do have quite a few components that have a lifetime measured in microseconds, right? I mean, that's quite phenomenal. And now as we kind of move to kind of serverless function architectures, I mean, you're actually going to need an atomic clock to measure the lifespan of these functions, right? And it's quite a literal statement, not metaphorical. So we've gone to a situation now where the digital stacks are much more modular, much more distributed, much more dynamic, and much more ephemeral. Well, now let's go back to that. Kind of architecture for monitoring systems. I mean, you can see almost from the description, it flat out doesn't work. Let's start out with the sampling, right? The first of all, the issue with the sampling only makes sense, and this is very important to remember, whether you're talking about IT or you're talking about vaccines, or you're talking about any kind of economic study. It makes sense only when you're sure that the population that you're trying to understand, that its characteristics can indeed be inferred from the characteristics of a very small part of the population. Now, with the modern IT systems we've built, that is no longer the case, precisely because they're so modular, right? Precisely because all the microservices, particularly the further they get away from one another, so to speak, the more and more independent they are of one another. So if you sample one part of the system, or you sample a couple of places around the system, you literally are not able to predict what's going to happen anywhere else. I mean, it's not that you're generalizing. It's not that you can't use the statistical methodologies, because the statistical methodologies, in some sense, already presuppose a commonality of structure, which in fact is not there. So first of all, the only way in which you can see what's happening to your system from end to end in any way that's at all accurate is literally by looking at all of the self-descriptive data that is being generated by the system. You basically have to get as much data about the system as you possibly can, and that data has to be super fine-grained, right? It has to really be able to kind of track the state changes that are taking place within the system, because you can't make inferences about what you can't see. Secondly, precisely because of the fact that these systems are continuously changing and the components are popping in and out of existence, right? That the idea that you can match whatever data you're taking against some kind of predefined model that is going to remain constant even during the course of the execution, let's say, of a single transaction with this system, it just no longer applies, right? It just doesn't. It doesn't work. The model is out of date even before you've loaded it, so to speak, into the your monitoring system. And what is the consequence of this? This is not just a theoretical issue. The consequence of this is that we are now, I mean, IT operations professionals, DevOps professionals are in a state where they're experiencing almost a continuous storm of alerts. They are continually being alerted that there is a mismatch between the sample data and the model. And of course, that makes sense, right? Because the model is basically meaningless, and the ability of the sample data to match whatever predictions that model makes, if there are matches, it's basically going to be random, right? So, our IT ops professionals are continually being faced with alert storms. And one of the most complaints I hear again and again and again from enterprises that deploy monitoring systems, that deploy event management systems, is not only are they being flooded with events or or whether they're strictly event records or these events that are derived from anomalies in a metric stream or something like that, that not only are they being flooded with events, but they're getting a heck of a lot of noise in those events. There are an enormous number of false positives in those events. And that is, I think, and I'm sure that most of you listening, if you're coming from if you're a practitioner, with regard to kind of monitoring or observability in the DevOps world, the IT ops world, I can almost guarantee that you are experiencing these alert storms, and you're experiencing, in some sense, even the worst fact that you're being alerted and the alerts themselves are kind of largely noise. So the only way around this is an approach to monitoring that, on the one hand, is able to ingest data in a fine-grained data that matches the state changes in the system, does not sample the self-descriptive data, but rather ingests all of it. And then that's not enough. And this is kind of a critique that I have of a number of my colleagues in the DevOps world, because they'll buy the idea that, yes, we need new data types, we need new fine-grained data to match the, how shall I say, the complexity of the behavior of the systems that we're trying to manage. But then what they want to do, and it's natural, is say, okay, we'll get that data in here, and then we'll build our own kind of monitoring system. We'll get metrics, put them into Prometheus, and throw Grafana at it, and kind of do it ourselves. But I say that that itself is something that's not very effective, because both the data sets you're dealing with and the complexity of the system behavior that is generating those data sets is such that it is just too complex for naked human cognition, right? And so you need some kind of automated enhancement of that cognition in order to see the patterns in the self-descriptive data being generated by these underlying systems. And it is that combination of a reliance on a more granular, low-level data, which typically takes the form of metrics, traces, and logs, and the application of automated cognition technology, you can call it AI if you want, to these streams of data that makes up what observability actually is.
Gotcha. So there's a lot in there to unpack. let me try to identify some of the key points there. So one of the things you're saying is that there's just a large amount of change in the system, and so this traditional modeling approach doesn't work. So you have to come up with something different. And then the other is that the amount of information coming is so great, so vast, that a human can't really process it. Did I sort of summarize a lot of those points down?
Yeah, oh, absolutely. That's perfect.
Yeah, that's interesting. So what do you do about it? So what's the movement forward? What is observability? Where is it heading?
Okay, yeah, no, I think it's heading in a fairly clear direction. Now, our ability to deliver on it as an industry, of course, is that's still an open question. But I do see signs of progress, and I think that we collectively, whether we're vendors, whether we're users, whether we're influencers like the analyst community, are beginning to articulate the problem, in a practical way. And so the way I look at it is, first of all, as I was talking about just a few moments ago, we are indeed talking about new types of data, or repurposing perhaps sometimes of some old types of data, but it's certainly using the data in the new way. And in the sense that with traditional monitoring systems and just the way in which we thought about IT, and I think this goes back to the culture thing we were talking about in the beginning, Mike, that I'll make the claim now, and we can explore this more later, that observability, not just a new kind of technology, it's a very different way of even thinking about how human beings acquire knowledge, right? So, keep that in mind, that this does involve kind of a radical shift in the way in which we think about a lot. So put that on the shelf. We'll come back to that later. So first of all, new kinds of data or a new approach to data, so that we need data that is sufficiently fine-grained, as I said earlier, to match the fine-grained nature of the state changes that our highly modular, dynamic, distributed, ephemeral systems go through. And that means reliance on metrics. It means reliance on traces, the actual paths of communication that occur through the various microservices or functions that constitute a modern digital stack, and reliance on logs, the kind of the unstructured records, the unstructured diary that that a digital stack keeps of itself as it goes through its paces. That needs to be the fundamental data source, the fundamental streams of data, that we access in order to observe what's taking place within the system. Events are still useful, but events are secondary structure that in many cases can be built out of these streams of metrics, traces, and logs. And I think that's the way we've got to look at it, that kind of events are secondary, and what's fundamental are these, what have been called the 3 pillars of observability. So in terms of systems, right, in terms of technology, the first order of business, right, is ensuring that whatever you put in place or whatever you buy, that it is able to ingest effectively, in a timely enough way, streams of metrics, traces, and logs. And it's also important, by the way, that these streams effectively be open to one another, right? Because the metrics, traces, and logs are all giving you different perspectives on the underlying system. It's like the old story of the 4 blind men and the elephant, right? You bring the elephant into the town, and there are these 4 old wise men, and they're touching the elephant in different places, but they're all blind, so they can't see the elephant. And one touches the leg and says, "Oh my gosh, it's a huge tree." The other touches the trunk and says, "Oh my gosh, it's a snake." The other one touches the ear, says, "Ah, it's a leaf of the banyan tree," or whatever the case may be. And I think that if you just look at metrics, traces, and logs in isolation, you're going to end up with that issue. So, once again, a critical aspect of any system that you deploy, buy, whatever, is to ensure that not only are you ingesting these 3 basic types of data, but that you're ingesting them in such a way so that any further analysis that you do is able to access and all 3 of these streams in an integrated way. So that's step 1. Step 2, now we get to that automated cognition component, right? And I'll just call it AI, and I believe it is AI, and one can get into a philosophical discussion about this, but I'll defend this quite vigorously if challenged. But let's just call it for AI for now. And remember what I said earlier about there being the data sets being very voluminous and being noisy even in the best of circumstances. So when I look at what the AI is supposed to do, the first thing it needs to do is to clear up that data, right? The first thing it needs to do is to reduce the amount of noise in that data, reduce the duplications in that data, because unless you clean that data up, any further analysis that you do, and I don't care what you throw at it, it can be like a multi-layer neural network, it can be a support vector machine, it can be HAL 9000, right? And working with incredibly noisy, junky data is going to produce noisy, junky results. So the very first step, the very first set of algorithms that a platform needs to apply to this stream of data is the ability to filter out the noise, filter out the duplication. Now, once you've done that, Then you want to take the result and start doing some analysis, right? You want to start correlating the data items. You want to start finding those data items, those metrics, traces, logs that are talking about the same events. And you want to be able to then correlate the events that they're talking about. And there are many, many different ways of doing this correlation. And in fact, most of what we hear about when people talk about AI or machine learning in the commercial world at this point in time, they're really talking about correlation algorithms. And in fact, truth be told, if you, if you look at vendors that self-describe as AI ops vendors, or have an AI ops offering in their portfolio, very typically what they're offering, really, there's no noise reduction. They're just offering various kinds of correlation algorithms. And correlation's important. Like, you do want to find out, for example, that if you've got response time degradation in London and you've got, a sudden uptick in database accesses in New York, and they're happening at the same time, you want to know that they're happening at the same time, and there may possibly be some further relationship between them. So it is important. The correlation step is extremely, extremely important. As I say, it sustains many AI ops offerings, right? That's pretty much all they do. But of course, we all went, not all of us, but most of us that have dealt with, even very introductory statistics, have learned that correlation is not causation, right? Not just sufficient to learn that, 2 or 3 items take place at the same time or in the same place, or, share some property. You also need to understand, and very crucially, if you want to do something about anything that's been uncovered, you need to understand the causal relationships between the events or the data items that have been correlated during the second stage. So a third stage is the ability to do this causal analysis. And once again, I want to underscore that causal analysis is not just another form of correlation. Causal analysis involves a very, very different kind of mathematics. It requires a very, very different type of algorithm than the one doing the correlation. In order to know that when you're looking at the fact of response time degradation in London and a kind of, an overload of database usage in New York, to establish that the second one is causally related to the first one requires a whole different type of analysis. In fact, the guy who developed a lot of the mathematics that allows us to do genuine causal analysis, a guy named Judea Pearl, literally just won the Turing Prize, which is kind of like the Nobel Prize of computer science. He just won it, just a couple of months ago. Very, very significant stuff that he's done and others have done in this area. But the critical point being is that causal analysis, and I've already said this, I know, but you remember one thing from this talk, remember this: causal analysis is different from correlational analysis, and it is probably the most important element of this automated cognition that I'm talking about. Well, once you've got the causal analysis, then of course you need to bring together the groups of people, the assets, to actually do something about what has been revealed through the first 3 stages of your automated analytics. This collaboration stage, very, very important. Many vendors are getting into this space right now. It includes notification algorithms. It includes learning algorithms. And I think what we're seeing, particularly in the wake of the pandemic and the emergence of the virtual NOC, the focus on AI-driven collaboration has proven to be an incredibly critical element of DevOps management of the production environment, or traditional IT ops management of the production environment. And then the last component, kind of the 5th element in this workflow, so to speak, is of course the smart guidance of automated responses, right? So, the team has collaborated based upon the knowledge that they've gotten from the first 3 stages of the automated analytics. They're going to do stuff about it. Among the things that they're going to do about it, there will be automated dimensions, and you will have AI driving that. So when I look at what is required, right, to deploy observability the way it ought to be deployed, right, is first of all the ability to ingest these signals in the form of metrics, traces, and logs, and then to apply to that incoming stream a sequence of selection algorithms, of correlation algorithms, causal analysis algorithms, collaboration algorithms, and automated remediation algorithms. And of course, it's not just a linear stream, it's actually a cycle, because when you do that automated remediation, you have now changed the environment. You will initiate, as a result of that, new behaviors. Those new behaviors will drive new events, new issues that, of course, must then go through that 5-step process, right? So maybe a better way of thinking of it, not as a sequence, but think of it as a cycle. A serpent that eats its own tail, and I think that is a picture of what observability within the context of DevOps needs to be. But also, I want to make the point that it's not just a dream. It's not just a utopia. It's something that we're seeing, more and more vendors, as I say, kind of settle on this kind of architecture. Gartner has recently published a guide to what they call it a guide to AI ops platforms, but it basically follows that model. Forrester similarly has kind of a 5-step model and talks about its interaction with observability. So I think the kind of influencer world is taking this up. And as I say, there are products that are available on the market that come pretty close to kind of delivering that entire kind of capability. So I think that, of course, we have a lot of work to do, right? I mean, none of this is perfect. Even our conceptualization is still fuzzy, but I think that we're on our way there, certainly.
Yeah, excellent. So I was recently talking to a colleague, and he was talking about this production outage he had that lasted for several hours, and it turned out some innocuous, like, admin machine had filled up a disk, and it was not obvious that this admin machine was in any way related to, like, the website that was trying to be accessed. And so it'd be interesting to see if this process you're talking about could tease out that kind of I don't know if that's correlation or causation. In fact, that's actually maybe a good question, is what would that be if you were able to say, hey, this website's out because this disk's full?
Yeah, well, it's really it's all of it, right? And I think that's an important point, that these things are cumulative, right? And although I'm elevating causality in some sense over correlation, you couldn't have the causal analysis without the correlation. So, like in the case that you're talking about, certainly first you would need to clean up the data, right? Then you would need to correlate these different events, and then you would need to figure out which of these events are causally related to the others. But you bring up a point that I think is also very, very critical, particularly when we're talking about these highly modular, distributed, dynamic, and ephemeral environments. That the root cause, it's not only that the root cause of an outage or a brownout is difficult to find, it's that what constitutes a cause itself can be a very complex structure. I mean, it's not just one microservice that is misbehaving, right? It's not just like in the old days, oh, it was a bad router, right? Or it was a bad line of code if you were, in kind of application performance monitoring land. No, now you're talking about, actually it could be, a collection of complex behaviors among different microservices. And if you just looked at one microservice alone, it would not be acting necessarily anomalously, right? Or it would be acting within the bounds of normal behavior. But what ends up happening is that, if you think of normal behaviors like bell curves, right? If you've got 5 microservices that suddenly stop kind of behaving the way they would in the middle of the bell curve and are acting as they would on the kind of the outer arms of the bell curve, a couple of standard deviations away from from the median, from the average, I'm sorry, then you end up with what is collectively an anomalous behavior. So I think that one of the reasons why you need this kind of automated cognition is because the causal patterns themselves have become a lot more complex. It's no longer, once again, the case of looking at a topology diagram and kind of tracing something through to a problematic node. You're now looking, even when you're looking at causality, you're looking at very, very complex patterns of behavior.
Yeah, it sounds like you're kind of referring to something I've always called cascading failure. Like it's a combination of a bunch of failures together that really leads to the real problem. And sometimes just chasing down one of those problems doesn't give you the answer. I think that's what you're saying. And
yeah,
I've seen that in reality in all the environments I've had to work with, either as a developer supporting production or owning production environment. It's and these things actually could be system related or actually could be process related too. Like how does a bug get into production, right?
Yep.
Things that go wrong before the bug gets into production. And that's just one example. So understanding that that understanding that multiple things could be happening and understanding to observe all those things at the same time, I think is really critical.
Absolutely.
That's what I hear you saying, like that's the new world and that's what we should be doing. And it totally makes sense to me. I've lived in that old model sample world for a long time, and it always had the failing of the model never was accurate and the samples were hard to figure out which ones to use. So,
right.
And you'd only do that by, maybe whack-a-mole, right? Like, oh, we had
that's right. That's a brilliant description. Yeah.
Another production problem, then we'll change the samples, and you just keep going until you get something. All right. Well, I want to. We're running close to end of time. Just a few more minutes. So I want to make sure the audience gets a chance to ask any questions that they might have. We've covered most of the topic here. So, Jill, do we got anything from the audience?
Mike, I think Will covered things pretty well. We don't have any questions.
Yeah, that's great. Yeah, this has been really useful information, Will. And I think the one thing that I take out of this whole thing, us working together and ultimately doing this, is it's a paradigm shift in this. It's really a paradigm shift, and you really have to think differently than that model sample mindset and embrace that change. So.
Yeah, I think that's right. I mean, the word paradigm or the term paradigm shift, as we all know, tends to be overused. But I think we are actually sitting on what is a genuine, what Thomas Kuhn, the guy who thought it up, would recognize as a genuine paradigm shift. About, once again, it's not even a question just of what it means to monitor. It is also a question about, what it means to learn about the environment with which you're concerned. That it's not a question of, how shall I say, finding data and hoping the data points to a static structure in the environment. I think that's the way in which we envision even the way in which our brains work, but rather what it is, it's a question of, wrestling with these streams of data as we ingest them and discovering patterns in the data itself, right? So the patterns are not reflections of some world that lies behind the data, but rather the patterns are what emerge directly from the data itself. And consequently, just as the data streams evolve, the patterns will themselves evolve on a regular basis.
Yeah, that does sound right. So I want to thank you, Will, for joining us today. It's been great chatting with you. And I also want to thank the audience for coming, because without an audience, it doesn't make sense for us to be talking, really. So it just becomes a casual chat between the two of us. So I want to thank everyone that's part of this, including Jill and all the staff that helped make this happen. With that, I'll bid adieu to everyone. Have a good
Great.
day.
Bye, everyone.
Bye.
Great. Thank you, everyone. Bye-bye.